So there's a couple of things different in the lab than what you've seen in the video lectures and in the textbook. And you've probably already noticed that you got this circuit down here, which is the emitter tail circuit, that in the textbook was basically just a resistor. And this is a lot more complicated. So what we were trying to do with the emitter tail circuit is we were basically trying to get a certain amount of current down here that would then get split between the two transistors so that we would get an equal amount of current down each side. So we were using a resistor to try and get a bias current. Well, maybe it's just easier to just put a current source down here and use a current source. So this circuit here is actually a current source. Let me explain how that works. So let's grab it off here and maybe drag it down over here. Get rid of these pieces. Okay, so the way that this works is here we have 10 volts and we have current flowing down this path from 10 down to minus 10. And when it does, it goes through these two diodes, and so we will get a 0.7 volt drop across each diode, which means that the voltage between this point and this point will be 1.4 volts. So basically by putting two diodes in series, we've created a 1.4 volt source or fixed voltage. So that's down the left-hand side. A little bit of current goes into the base, and the base emitter drop has 0.7 volts. So we'll lose from that 1.4 volts, we'll lose 0.7 of it, and we'll end up with a fixed voltage across this resistor of 0.7 volts. Well, if the voltage across this resistor is fixed, then the current through it is also fixed. And if it's 0.7 volts across a 75 ohm, then the emitter current here would be 0.7 over 75 ohms. That is approximately 9 milliamps. So the 9 milliamps is what's going to get split between the two upper transistors, and you'll get 4.5 each. So we've created, using a little current source circuit, we've created a fixed current source, a relatively fixed current source, much better than the resistor. So that's one thing that it does. The other thing that it does, if you recall from the AC analysis in the video lectures, when we went to figure out gain, we said that gain would be V out over V in, and V out would be RC, IC, RC. So using this one, for example, V out would be IC, RC, the current through this resistor times its resistance value. So that would be V out, and V in would be this voltage over here, and current would flow this way. And so we said that V in would be IE times R prime E plus R prime E. And when we did that, we ignored this resistor because it was 7K and it was much larger than R prime E, and so we said we could ignore it. Well, if we replace that with a current source, if we take RE out and we replace that with a current source, well, when we Thevenize it, then the current source becomes an open circuit and the gain becomes exactly this. It's still an approximation because we ignore the beta and beta plus 1, but with a current source, the gain becomes RC over 2R prime E single-ended. So that's the single-ended gain, and then the double-ended gain would be twice that, so that would give you your double-ended gain. The other change that we made to this circuit to make it a little bit easier to do in class is we added a couple of resistors on the base of the transistors. What this does is it reduces gain quite a bit so that you can get the signal generator low enough so that you can put in a signal and see an amplified signal. On its own, the Diff Amp has a large enough gain. We can't get the generator down to a small enough voltage to input it. So we've added a couple of resistors. So how do these resistors reduce gain? Well, let's take a look. So those resistors here and here are basically, one is here and one is here. So how does that affect the gain? Well, if you remember previously, gain AV was V out over V in, and we worked it out to RC over 2R prime E, so it's about 100. Once we put these resistors in, we can figure out the gain again, and we need to write equations for V out and V in. So V out is basically the same. V out equals ICRC, so that's the same. But V in, I'm going to look at it this way. So let's say that V in, when you apply a signal, current flows this way to ground. Remember that the current source is an open circuit, so now the current goes that way. It goes this way from the generator to ground. It goes through R1, creates a voltage across R1. It goes through R prime E here, creates voltage drop across it. Same with this one, second R prime E, and then the last base resistor. So we could say that V in is VR1 plus VRE plus VRE plus VR2. It's the sum of those four voltages. And then what we can do is we can write those four voltages in terms of transistor currents. So the voltage across the first resistor is just the base current times R1. And then R prime E, these R prime E's have the emitter current going through them. So it's IE R prime E, IE R prime E. And then the last transistor also has, or sorry, the last resistor also has an IB. So it's IB R2. So here we've written V in terms of all four of those resistors. We need to put them into a common term. Easiest thing to do is probably divide IB by beta. So if we substitute, we take IB and we replace it with IE over beta, there and there. And then we group the common terms, bring them out front. We get IE V in equals IE times R1 over beta plus R prime E plus R prime E plus R2 over beta. Well, R prime E's with a beta of 200, they're going to be about 5. R1 is a 1K. If beta is 200, that's going to be 5. And this is also going to be 5. So this adds up to 20 ohms. And when I put that in here, AV equals V out over V in. ICRC over IE times 20. IC and RC are like 200 over 201, cancel, cancel. 1K over 20. You should get a gain of about 50 with those resistors in. And I think that most students, when they do the measurement in class, they get a measurement of about 42 in around there. So that is the value that you're expecting. And we got that by adding in these resistors here. We were able to get that down to that value with these resistors. And that's what you should measure as your single-ended gain. So that should be your gain from here. That should be your gain from here compared to the input voltage. If you put your load across both outputs, then the gain will be 2 times 42, because what's happening, if you put it across both, what's happening is you're wiggling this side, which is 42 times bigger than what came in, and you're wiggling the other side. Instead of holding it at ground, you're wiggling the other side in the opposite direction. So when this is minus 42, this is plus 42, and there should be 84 times the voltage across there.